Okay, so welcome back to this next video on the mechanism of action of chloramphenicol, which is also called chlornitromycin. Chlornitromycin, I believe, is the old name, and chloramphenicol is the more new name. Right, okay, so far we are discussing the process of translation because chloramphenicol or chlornitromycin is an inhibitor of the translation process and therefore stops protein synthesis. And in order to understand how it blocks translation, we need to understand the mechanism of translation. So we are looking at translation in bacteria. And in fact, this mechanism of translation is actually very similar in eukaryotes. It's been far more studied in prokaryotes, but it's pretty similar in eukaryotes. Okay, so far we are at the stage of having a 30S initiation complex, which is this 30S ribosomal subunit bound to initiation factor 1, 2, and a GTP molecule, along with an mRNA, which is bound to the 30S subunit via its Shine-Dalgarno sequence, shown here in orange, and which also has a start codon around 5 to 10 organic bases downstream of the Shine-Dalgarno sequence, which is now bound to a 4-methionine tRNA, so an F-met tRNA, basically. Okay, what's going to happen next is that the 50S ribosomal subunit, remember I told you right at the beginning that the ribosome consists of two subunits, the 30S subunit and the 50S subunit linked together. So far we've only talked about the 30S ribosomal subunit. It's now time to add the 50S ribosomal subunit. And basically it's going to come from this side and bind on. Okay, so let's draw that happening. So we'll draw it, we'll try and squash it in down here. Okay, and basically when the 50S ribosomal subunit does bind, it causes the initiation factor 1 and initiation factor 2 to cleave off from the 30S subunit. So they cleave off. Also, this GTP molecule is going to be hydrolyzed to GDP and inorganic phosphate. Okay, so here is the 30S ribosomal subunit, now no longer with its initiation factor 1 and its initiation factor 2, and no longer with this GTP, which has now been cleaved into GDP and inorganic phosphate and has gone off into the wilderness. Okay, so here is our mRNA still bound here, okay, with its Shine-Dalgarno sequence here, and its start codon, which I'm going to draw slightly bigger now. So there, I'll color code them so that we don't get confused. So this is the start codon in pink, and this is the Shine-Dalgarno sequence here. And now, what's happened is this 50S ribosomal subunit has come and bound down here to make the full 70S ribosomal prokaryotic ribosome. And now, from this start codon, you still have bound the 4-methionine tRNA here. So this is the 4-methionine tRNA. So now this whole structure is now known as the 70S initiation complex. And now basically we are ready to elongate and to begin translation basically. So far we've just prepared for translation. This is now the point at which we're ready to begin translation. Okay, so before we can discuss translation, there's something I need to discuss with you. The ribosome basically has 3 sockets in which tRNAs can sit, basically. So there's this first, so I'll do this in green just to show them. There's 3 sockets, effectively. A socket here. I don't know if this is going to show up, actually. Maybe I should do it in full green. There we go. Rather than... So there's 3 sockets. So I've just drawn it all as one at the moment. But there's the 3 sites, basically. There are 3 sites where tRNAs can all sit and be bound to the mRNA. So at the moment, we've only got 1 tRNA molecule in one of these sites, and so we've only got 1 tRNA bound to the mRNA. But you could have another tRNA sitting here bound to another codon downstream of the start codon, and you could have another tRNA sitting up here more upstream. So these 3 sites are known as the A site here, this one where tRNA is, well, what we're going to find out, tRNA is going to come in here. this P site in the middle, which is known as P because it's the Peptidyl Transferase site, and this isn't showing up very well, so I'll draw them up here. So this is the A site here, this is the P site because the Peptidyl Transferase enzyme is near here, and then finally this final site is the E site, which is where tRNAs exit basically. So they leave the ribosome from this site. So they come in the A site, they move into the P site, and they're going to move out from the E site. So the way people often remember that is it's APE, A-P-E. Okay, right, so then we have the 70S initiation complex. We now need to discuss how we elongate this, well, how we even build a polypeptide, because at the moment we've only got a single amino acid. So we need to discuss how we're going to actually build our polypeptide. Right, okay, so let's redraw the picture and add a few things in now. So here's our 30S ribosomal subunit here. So this is the 30S. Then we've got the mRNA bound here, like so. And we've got the Shine-Dalgarno sequence still here at the moment. Then we've got this start codon, and then we've got the next codon. So that's the thing that I'm adding on now. That's the important addition, because how are we going to elongate? Well, we're going to look to the next codon downstream of the start codon, basically. So here's the 50S. So let me color code everything back in. Okay, so this is the Shine-Dalgarno sequence here in orange. This is the start codon here in pink, 5 to 10 amino organic bases downstream of the Shine-Dalgarno sequence. And then this neighboring portion here, and there's no gap in between these. The codon follows straight on, basically. So you've got 3 organic bases here, then the next 3 organic bases make up this next codon, the second codon, basically. Okay, and we know we've got this organic base, this tRNA sitting here with this 4-methionine on here. Right, and that's the P site, here's the A site, and here's the E site. So basically what we need to do is we need to bring in our next tRNA with its amino acid, which is known as an amino-acyl tRNA, which is just the general name for a tRNA with an amino acid attached to it. We need to bring in our next amino-acyl tRNA, which is complementary to the codon of this next second codon. So basically, let's say this is your second codon here. So you have 3 organic bases here, which could be anything basically, and then what you need to do is you need to make a tRNA, you need a tRNA that is complementary to that, which has the complementary anticodon here, and that tRNA basically will have a specific amino acid attached to it that is specific to that anticodon, and therefore is specific to this initial codon in the mRNA. And that amino-acyl tRNA needs to come into this A site, basically. So this is known as an amino-acyl tRNA, basically. Okay, now you don't just let amino-acyl tRNAs enter the A site without guidance, basically. They don't come in on their own. They come in with another protein associated with them. And this other protein is there to make sure that you do not put in the wrong tRNA here, i.e. that you do not force in a tRNA in here that doesn't actually have the complementary anticodon to the codon that is here in the mRNA, i.e. it makes sure that you are actually putting the correct one into this A socket, basically. Okay, so this protein that does this is attached to the amino-acyl tRNAs, and it's known as elongation factor TU. So this protein here, let me just label it up, is called elongation factor TU. Right, and it's also bound to GTP. So elongation factor TU with a GTP molecule attached to it. Now, basically, what happens is the amino-acyl tRNA with this elongation factor TU and the GTP molecule come in. They go into this A site, so let's draw that happening. And if the anticodon on this amino acyl tRNA is actually complementary to the codon in the mRNA, then this protein, elongation factor TU, basically it cleaves off from the amino acyl tRNA, and also in that process of cleaving off, the GTP molecule is hydrolyzed to GDP. So what you end up with is the amino acyl tRNA remains in the A site, but now this elongation factor TU goes off with its GDP now, because the phosphate's fallen off, basically cleaved off, and you also produce an inorganic phosphate out of that process. Right, so if you somehow manage to put an amino acyl tRNA into the A site that is not complementary to the codon on the mRNA, then the elongation factor TU will not break off, and basically you will stop that from you from putting in that incorrect tRNA. It will come back out basically eventually. Okay, so this is a protection mechanism against making faulty proteins, basically. So that's that process. I just want to quickly discuss how we regenerate the elongation factor TU GDP into amino acyl tRNAs with elongation factor TU and GTP. So basically what you do is you bind this elongation factor TU protein to another elongation factor known as elongation factor TS. So TU and TS bind together, and when TU and TS bind together, TU gives up that GDP molecule, so GDP goes off. So what happens is TS comes over here, it throws that GDP off, and it binds to the TU instead. Now, this elongation factor TS, and I should write its name out, I should do it that courtesy, elongation factor TS. This elongation factor TS then assists the elongation factor TU in finding another GTP molecule, and also in finding another amino acyl tRNA. So, it also finds the tRNA here, with an amino acid here. So basically it helps the TU to find the amino acyl tRNA again and another GTP molecule, and once the TU has got both of those back again, it regenerates this, and then the TS falls off, so TS falls off. So elongation factor TS is very important in regenerating the amino acyl tRNA bonded to the elongation factor TU and GTP. Okay, right. So that's that regeneration process talked about. Now let's talk about the actual elongation process of the polypeptide. Okay, so we brought in this next amino acyl tRNA here, and it's now in the A site. Now, the amino acid here, which is 4-malmethionine, and the amino acid here need to now join together. So remember I told you that the way that this 4-malmethionine is linked to this tRNA is via the carboxyl terminus of the 4-malmethionine. Well, basically, what you do is you cleave that bond between the carboxyl terminus of the 4-malmethionine and the tRNA, and instead you bind the carboxyl terminus of this amino acid onto the amino terminus of this next amino acid, basically. Okay, so let me draw a bit of that out. So, let's say these are our two tRNAs like this. So we've got our two tRNAs, one in this P site, which is this 4-malmethionine tRNA, and one in our A site. And basically, the amino acid is joined in some way via its carboxyl terminus. So I'll draw this. So here's the carboxyl terminus of this 4-malmethionine. Here's the alpha carbon. Here's the R group of our 4-malmethionine. So remember these two methylene groups and then the methyl group on the end of that sulfur. So don't rush this drawing, otherwise it will look shoddy. Okay, so here's the methionine group here, and off that alpha carbon you also have this hydrogen, and then you have this amino group which we know is linked to this 4-mal group here, formic acid. Okay, now over here you're going to have some other amino acid here, which might have any old R group. We don't know what amino acid it is. All we do know is that it's certainly not methionine, because methionine is only used as the first amino acid. And then you have this free amino group. And basically what you are going to do is you're going to cut this bond here, and you're going to attach that carbon to this nitrogen here. You're going to cut off one of these hydrogens, and you're going to transfer this hydrogen onto the tRNA, which has lost the 4-mile methionine, and then you'll transfer the carbon onto that nitrogen, basically. And that will form you a peptide link between this first amino acid, this 4-mile methionine, and this second amino acid. So, in a more cartoon sense, what will happen is, if we're using these balls to represent the amino acids, then if this is the amino acyl tRNA in the P site, i.e. our 4-mile methionine tRNA, and if this is our amino acyl tRNA in the A site, then what will happen is it will go from looking like that to looking like this. The tRNA in the P site will now be empty, it won't have an amino acyl group, and the tRNA in the A site will now have 2 amino acids bound to it. It will have a little dipeptide bound to it, effectively. So you'll have this, and then it will go on to this. Okay, so it's got a dipeptide there now. Okay, now the enzyme which catalyzes this reaction, so this is our dipeptide, the enzyme which catalyzes this reaction sits basically at the bottom of the 50S ribosome. So here's the enzyme which is going to catalyze this reaction, and this is very important because this is the enzyme which chloramphenicol inhibits, basically. It's called peptidyl transferase. So this enzyme here, which transfers the amino acid, or it may well be a whole polypeptide by now, it transfers this amino acid from this tRNA in the P site to the tRNA in the A site. Its name is peptidyl transferase. And basically what happens if you give someone chloramphenicol, if you expose the bacteria to chloramphenicol or Chlornitromycin, I'm learning how to say that now, chloramphenicol or Chlornitromycin, then it goes in and it binds to this peptidyl transferase and it stops it from working. And that is how you halt protein synthesis, because this peptidyl transferase, this binding of the amino acids together, that's the foundations of what translation is all about, the forging of these peptide links between these amino acids. And if you have blocked the enzyme which does that, then you're not going to be able to link amino acids together, and you're going to get total failure in translation. Now, we've got to the end of the story, really, with regards to chloramphenicol or Chlornitromycin, but we aren't really at the end of the story for translation, so I want to continue the story of translation just to finish it, but that's how chloramphenicol or /Chlornitromycin works. So we'll continue this discussion in the next video.